Okay, so yesterday when we looked at the number of electrons in the conduction band, we came up with this expression. And even today when we were just doing the previous derivation, we used this expression. So what is the expression? Nc e to the power Ef minus Ec by kBt. Now we just derived a different expression for Ef, right, which is in terms of Ec and Ed. So let us try substituting this expansion for Ef in this expression to see what we get. So Nc into e to the power Ef minus Ec by kBt, where instead of Ef we make this substitution. So Ef is equal to this, Ef minus Ec will be this minus Ec. So when you take LCM and substitute, you get this. Ef minus Ec by kBt will be this term, e to the power that will be this. So the final expression will be Nc into e to the power Ef minus Ec by kBt, which is Nc into this expression. So finally you get root of Nc Nd e to the power Ed minus Ec by 2 kBt. So what have we done here? The number of electrons in the conduction band Nn. This is what we initially started out to find. So we first equated this to the number of ionized phosphorus atoms or number of ionized donor atoms, and we took the logarithm and did all that, and we got one expression for Ef. Now we take that same Ef expression and we plug it back into this equation. Then all this is simple math. You take the LCM at this point, and then you take kBt in the denominator, then you put e to the power and the ln gets cancelled, then cancelling of square root and Nc in the numerator. It's all just pure math. So finally what we started out to find out was the number of electrons in the conduction band. This is the expression we have, root of Nc Nd e to the power Ed minus Ec by 2 kBt, where Nc is a constant we looked at in yesterday's derivation. Nd is the number of donor atoms totally, e to the power Ed minus Ec, where Ed is the donor energy level, Ec is the conduction band energy level, K is the Boltzmann constant, and T is temperature. So Nn is root of Nc Nd e to the power Ed minus Ec by 2 kBt. And Nc, this is the expansion. How did we get this? We saw this in yesterday's derivation on intrinsic semiconductors. So you plug this expansion back in, you take all the constants out. The final expression for number of donor electrons in the conduction band is 2 Nd whole raised to 1 by 2, 2 pi me star kBt upon h square whole power 3 by 4, e raised to Ed minus Ec by 2 kBt. So this derivation was purely math. The only physics idea we applied here was you take this initial expression and then you plug in the value of Ef. After that it's pure math. So what is the important thing to remember from this expression? At low temperatures, meaning as long as the donor electrons are getting ionized, the donor atoms are getting ionized and the donor electron is moving to conduction band, in those temperatures the number of electrons in the conduction band is proportional to square root of donor impurity density. So Nn is proportional to square root of Nd. When everything gets ionized, Nn equal to Nd, meaning from every phosphorus atom the electron has gone there. So the number of ionized atoms is equal to the number of electrons there. So Nn is equal to Nd.